This video we're going to look at processor fundamentals. It's 4.1 of the CIE 9618, but a lot of the exam boards cover the same sort of material. We look at the von Neumann architecture, and this is one of the approaches we can take to computer system design. It's an early approach, and it's the basis for most computers these days. Before the von Neumann design, most computers had to be wired or built to do a particular task, and it was difficult to reprogram them to do different things. So von Neumann came up with a design for a system in which the data and instructions are both stored in a single memory unit, and they're stored as binary. So data and instructions are binary in a single memory unit, a single physical memory unit. Introduced this idea of a stored program concept. A stored program means that you can load programs and run them without actually having to change the hardware. So the computer then becomes flexible, and you can change it to run whatever programs you want. Within the von Neumann architecture, we have a number of components to know. These include the registers, clock, the arithmetic logic unit, the control unit, data, control and address buses, and the memory unit. So what are registers? These are very small amounts of fast memory. They're the fastest kind of memory, and they're the smallest. So sometimes you'll see pyramids of memory, and registers are at the top of the pyramid as the smallest and fastest type of memory. We have a couple of types of registers: general purpose registers and special registers. The general purpose ones can be used for all kinds of different things. Special registers have one particular purpose, and it's the special registers that you need to know by name. And they are the PC or program counter. That stores the address of the next instruction. The memory data register, which stores data from or going to memory. The memory address register, that stores the address of the data that you want to fetch, or the address of where you're going to write some data. The accumulator, which stores the result of the most recent operation. An index register, and this is used when we're calculating address locations. The current instruction register, which holds the instruction we're currently working on. And a status register, which holds a number of flags to indicate things like overflows. So if you look at the clock is there to regulate execution of instructions. And in a modern CPU, for example, in a in a personal computer, you'd find your clock running around about 4 gigahertz. Of course, hertz is a measure of frequency, and gigahertz means, in this case, 1000 million. So 4 gigahertz would be ticking, so to speak, every 4,000 million times every second. And on each tick of the clock, some more work can be done. Not necessarily an entire instruction, depends on the architecture we'll look at more later, but some more work can be done on every tick of that clock. So whilst the piece of work that's done may be very small, it ticks a very large number of times every second, which is why computers are so powerful and fast at doing calculations. The arithmetic logic is a really important part of the CPU. It's where all the arithmetic and logical operations are carried out. So there are circuits there that will carry out those kind of operations. And the arithmetic logic unit does what it's told by the control unit. So it's basically a slave to control unit that tells it what to actually carry out. So the control unit itself oversees the whole execution process and everything that's going on within the CPU. Its speed is regulated by the clock, so the control unit uses the clock directly. It decodes instructions first to work out what they mean, because instructions are quite complicated and it needs to know what they actually mean. and then it uses the ALU if it needs to. Not every instruction needs the ALU, but the majority would. And it uses the control bus to coordinate the other components involved. We'll come on to buses shortly. So we've got 3 buses. A bus is just a set of parallel wires connecting 2 components together. So if you want to join, for example, the memory unit and the CPU, you can create parallel wires called a bus in between the 2. So the 3 buses are the data bus, address bus, and control bus. The data bus is used to transfer data and instructions between the memory unit and the CPU. It's a bidirectional bus, which means data can be traveling in either direction, but only one direction at a time. The address bus carries addresses only, and it carries addresses from the CPU always to the memory unit, never the other way around. So the address bus is unidirectional. The control bus carries control signals that are sent between components. This could be things like read-write signals, clock signals, interrupt signals, and so on. And those buses, that bus, the control bus, is a bidirectional bus as well. So the memory unit in von Neumann's architecture sometimes is referred to as different things. It's really confusing. There are so many names for it. But we can call it primary memory or primary storage, main memory or main storage. CIE like to call it immediate access store, and it's also generally referred to as RAM because that's what we use for it now. Whatever the name though, the memory unit stores data and instructions in the same memory unit, and these can be directly accessed by the CPU. There are other types of architecture when there was more than one memory unit. For example, Harvard architecture has separate ones for data and instructions, but von Neumann, it's important to remember that they're using the same one. So this is what it could be represented as. We have the clock there doing system timing. That feeds into the CPU. Within the CPU, you've got all the registers, the program counter, the MAR, MDR, CIR, accumulator, index register, status register. So they're all the special purpose registers. Then you've got the control unit and the arithmetic logic unit. It shows here the address bus between CPU and memory, only going from CPU to memory. This is why it's a one-way arrow. The data bus it shows is going both ways, because data can be read from or written to memory. And then the control bus. This is quite a simplification because the control bus connects up various things, but it just indicates that there is a control bus and it is bidirectional. So the CPU is carrying out what's called the fetch execute cycle. Different places call it different things. Some people call it fetch decode execute cycle, FDE. Some people call it fetch decode execute, FDX. CIE like to call it fetch execute, just fetch execute. So what happens as soon as your computer is turned on, it will try and fetch the very first instruction. That will normally come from ROM in a general purpose computer that we're used to. So it always goes to the same place in ROM to get that first instruction. From then on, it's going to do the cycle. So it's going to get that instruction, work out what it wants to do, and then execute it and do it, and then go around again and again. So the step 1 is fetch an instruction, second step is decode it, work out what it means, and then the third step is execute it, and then we go round and round again. And this carries on until the computer's turned off again. So in a little bit more detail with registers, we can look at the cycle like this. So the very first thing we typically do in sort of middle of the cycle is we're going to look at the program counter first for the next stage of this continuous cycle. So the program counter contains the address of the next instruction. So we need to get that and put that in the MAR, because the MAR contains the address of anything that we want to get from memory. Immediately, or at the same time potentially, the program counter can be incremented to indicate the next instruction in memory. So it's ready already. As soon as we've fetched one, we can indicate that where the next one's going to come from. Then the contents of the MAR will travel along the address bus, so they're traveling from the CPU to the memory unit, and then it will look up and find the data at that address. Now, in this case, the data is an instruction. That instruction is then placed on the data bus by the memory unit and then passed back to the CPU. The data that arrives back at the CPU from the data bus is placed in the MDR, the memory data register. Sometimes it's referred to as the MBR, the memory buffer register, but it's the same thing. So once the instruction is in the MDR, it can be moved into the CIR, the current instruction register, ready to be decoded and executed. So the CIR is looked at by the control unit to decode it, and then the CU may tell the ALU, the arithmetic logic unit, to carry out that instruction. And then the result of the operation is likely to be stored in the, it's a mistake on the slide there. So it should be, a result of the operation can be stored in the accumulator, the ACC. You can write this sort of thing down in a shorthand called register notation. It's a bit long to describe it in words. So there's this notation. There's various symbols, and here are their meanings. So square brackets is used to indicate this means the contents of. So if you said something like PC in the square brackets, that would mean the contents of the program counter itself. The arrow is replaced by or becomes, so the value on the right is moved into whatever's on the left. Double brackets means that you have to use the address to find the value that you want. So the contents of the memory location whose address is held in that is used. So for example, if you put the if you put the MAR in the middle there, that means you don't want the actual contents of the MAR, you want the contents of the address that pointed to by the MAR. And a comma separates the operations. You can actually put two things on the same line to indicate that they happen at the same time. So reading the notation, for example, here we've got MAR, arrow, and then square brackets PC. This means that the contents of the PC, indicated by this fact it's got square brackets around it, that means the contents of the program counter are going to be moved into the MAR. So it goes from the right to the left, moving the data that way. The second one is slightly different. Like I said, we've got the MAR in there. So the first square brackets means get the contents of the MAR, which is an address, and the second lot of brackets mean use that address to find some data and move that data into the MDR. And finally, we've got an increment of the program counter. So again, we refer to the contents of the program counter by putting it in square brackets, and then we say add 1 to that, and then that whole thing is evaluated and moved over to the left and overwrites the program counter. So a fetch operation that we described earlier in words can be described with this notation. The first step is to get the contents of the program counter, move that into the MAR. Then, at the same time, we can increment the program counter to prepare it and point to the next instruction in memory. Then we'll take whatever's pointed to by the MAR, some data that's pointed to by an address in the MAR, and move that into the MDR. And then the MDR, the data can be moved into the CIR. And obviously in this case, because it's a fetch, that data would effectively be an instruction. we can write steps 1 and 2, the first two steps, on the same line separated by a comma to indicate that they could happen in the same clock cycle. Because there's no dependency there, they can be done in parallel. So a number of things affect the performance of your system. Some of them we look at in this course. If we change things, we can affect the performance. And performance in this case means basically the throughput, how much work can we get done in a set period of time. Obviously, improving performance means getting more work done in that period of time. And the things we look at for CIE that affect performance are the processor type and number of cores, the bus width, the clock speed, the amount and speed of cache. So let's have a look at those. A core, or processor core, is a part of a CPU that can carry out the fetch execute cycle independently or somewhat independently of the other cores. That means you can do multiple instructions in parallel, so you're working on different bits of work at the same time rather than having to do one after the other. So if you can use that, it's clearly an improvement on performance, because we can be doing, say, 4 things at a time in a quad-core CPU rather than just one and then have to wait and do the next one and the next one and the next one. Each core can have its own cache, which is fast memory for storing frequently and recently used data instructions. Not all software can take advantage of multiple cores though, which is one reason why having a multi-core CPU isn't always going to give you a massive performance increase. It can do, and it often will, but not always. And there's lots of other factors involved, of course. So if you're comparing 2 separate systems, one with a quad core and one with a single core, the quad core may not be faster at all, depending on the other factors. For example, the clock speed, the amount of cache, and so on. So let's look at clock speed. Increasing the clock speed means that the FE cycle can be carried out more quickly, so we get more cycles done in a given period of time. And because each one of those is doing some work, that means that we get an increased performance. If you want to increase the clock speed above what's normally provided when, say, the computer ships, it's called overclocking, and you can pretty safely overclock most CPUs because they're clocked on the conservative side. But if you clock too much, you can cause heat issues, the CPU can become unstable, and it can reduce the life of the CPU. But it does make performance increase. We mentioned cache earlier. Cache is high-speed memory. You often have different levels of cache, like level 1 cache, level 2 cache, and so on. And some of these are on the CPU and sometimes they're off the CPU. But all cache there is basically, all cache is there essentially to provide for frequently and recently used instructions so that you can get them more quickly. If they weren't in cache, if they weren't available in cache, you'd have to go to RAM to get them. And going off to RAM is slower than going into cache. So if you increase the cache size, then you have more likelihood or increased probability that you'll find the data instructions that you want in cache and not have to go to RAM as often. Therefore, you're not waiting or not doing slow memory accesses, and therefore performance increases. You can also increase the speed of cache, have better cache in your design. Obviously it'd be more expensive, but it will improve performance again. Now, bus width does affect performance. Remember, a bus is just a set of parallel wires between 2 components, like the CPU and the memory unit. So if we have a wider bus, we have more parallel wires and we can send more data at the same time, i.e. in parallel. It also affects the size of instructions. So a single instruction could now store the data that it needs as well as the instruction, or is more likely to be able to store the data. And therefore we don't have to do separate fetch instructions or load instructions to go and get the data that we would need. So we can potentially do it with one instruction rather than multiple instructions. Increasing bus width also allows you to have larger memory address values because the address bus, for example, if that's wider, then we can actually send larger number values on it, which can address a larger memory space. Okay, peripherals. So peripherals are just devices that can be connected to a computer. It's called a peripheral basically because it was conceptually on the edge, on the outside of a computer. But nowadays it's just anything that you can plug in to a computer. There are several standards. There are lots. There are a few that CIE want you to know. These are the USB, HDMI, and VGA. So they're all different kinds of connections, and they just want you to be able to make some comparisons between them. So the first big difference is between VGA and the others. VGA is an old, fairly obsolete method of graphics connection, and it used analog signals. Nowadays, everything is digital, or pretty much everything we use is a digital interface, but VGA was analog. It's one of the reasons why you often used to get poor image quality on VGA monitors and screens because of the fact that it was converting backwards and forwards to analog and digital. Whereas nowadays it's the entire loop is in digital format. USB is a general purpose interface, not specifically for any one thing. HDMI and VGA are both specifically about displays, and in the case of HDMI, audio. A good difference to say between HDMI and VGA is HDMI doesn't need a separate audio cable, whereas VGA does. So HDMI is obviously a multimedia interface. That's one way of remembering the fact that it's got video and audio built in. And then USB is also capable of providing power, for example, for charging, where the others aren't used for that. Okay, so interrupts. Interrupts are necessary because sometimes we want to stop a program that's executing. Remember, it's going through this fetch execute cycle continuously, so a never-ending process of trying to find out what the next thing is and do it and do it and do it. But sometimes we want to suspend or stop what's currently being done in order to do something else. There may be something that really needs the CPU's attention, and we need a way of being able to do that. So we use interrupts. An interrupt is effectively just a signal that's sent to the processor, and then the processor suspends the current sequence of instructions and deals with the interrupt. And after the interrupt's been dealt with, the sequence that was interrupted can be resumed again. Interrupts can have priorities such that only a higher priority interrupt can suspend a task. So if it's already doing something really important, it's not going to be interrupted by something not so important. Interrupts are checked for at the end of a cycle. In the exams you can say at the start or at the end. It effectively means the same thing. It's not mid-cycle, it has to be at the end or before. Interrupts can be caused by various things. For example, a hardware interrupt, a peripheral device might need some attention. Just pressing a key on a keyboard requires interrupts. Mouse clicks, printers running out of paper and so on are all done with interrupts. We don't want to be constantly polling the keyboard to see if something's been pressed. That would be a waste of time processing. So we do it such that the hardware actually interrupts the CPU and says, hey, I've got something you need to deal with. Timer interrupts, so we can have hardware timers that raise an interrupt at the end of that period of time. So for example, we can have in a multitasking system with various programs that want to run, we can make it so that a program has to stop after a certain period of time and then give another task a chance to run for a while. Software programs, they can generate their own interrupts. For example, you might have code that you've written that uses some code that's part of the operating system, i.e. a system call. In order to use that operating system service, you interrupt your own program, and then effectively control will be passed to the system software. You can get interrupts through hardware faults and errors. So if something goes wrong, if something's something's broken, or you've got a fault, or you've done a software error like division by zero, then you can raise an interrupt to handle it. The idea is you want to handle it in a safe and sensible way, rather than just let it all go wrong. Power failure. So some systems trigger an interrupt when power is running very low, so it can quickly try and save critical data before the power completely runs out. So we use interrupts quite a lot for input-output devices, for multitasking, allowing multitasking to happen. Use it in real-time systems, so we can respond to sensor input when it occurs and do something about it, because we have to do that with quickly. We can't wait a long time before that happens. For error handling and exception handling, and for power management. And there's a diagram there that shows the fact that we have to do the fetch, decode, execute. We allow an instruction to complete when an interrupt occurs, so we don't stop halfway through executing an instruction. Typically we let the thing complete and then we check for interrupts, and if it is an interrupt, we go and use what's called an interrupt service routine, which is just code that will handle the interrupt, and then if there isn't an interrupt when we check, we'll just go around and continue the cycle as normal. So the interrupt service routine is a program, could be part of the operating system or a device driver, that runs when you need to handle a particular interrupt. So if you're reading character from keyboard, buffer, or writing something to a printer, then there'll be a specific interrupt service routine for it. The CPU, we need to work out which interrupt service routine to run. So we need to look at something called an interrupt vector table and look at the interrupt type, and then work out the right interrupt service routine to run. When we interrupt a process, what we do is we save some of the registers and contents onto a stack. It's called an interrupt stack. This is just a data structure where we can go and get data back again later, so that when we need to restore the task that was running before the interrupt, we can get back all the contents of the registers that we need and then continue as if nothing had happened, right? So it doesn't lose anything or lose track of what it was doing before. So the sequence is, again, first of all you let the current instruction complete, then you check for the interrupt flag, then save the current state, including registers like the program counter, and put that on the stack. We're using a stack because a stack is last in, first out. So the last thing that was running when we got interrupted is going to be the first thing that's taken off and used when we resume. We find the correct interrupt service routine. We pass control to that interrupt service routine and execute that. And once that's finished, we can restore the save state or the most recent state on the stack, and then that will be resuming the original program. Like I said earlier, interrupts can have different priorities. Some things are very urgent, like power failures are going to be more important than, say, keyboard inputs. Uh, Systems can often support many levels of priority, so that they can all work at different levels. There's an interrupt enable disable flag, so it can be set to indicate that you can no longer interrupt a task. The task may be critical, it must be allowed to complete and cannot be interrupted, in which case you would disable the interrupt flag. And as we said, we're using a stack because its last in, first out structure supports the kind of process that we're doing, where we want to go back to the most recent thing that was running after an interrupt. Okay, that's 4.1, and in the next section, 4.2, we'll look at assembly language.